Assalamu alaikum. Welcome to the next chapter. In this class, we will continue what we have done in the previous class. So, in the previous class, we discussed how to form the equation in this type of the matrix. So, what we did, we'll have a little bit of recap of that. We formed the equation, and the equation are formed on the basis of the specified real power and reactive power. We know that a real power is specified for all the buses except the slack bus, and reactive power is specified for all the PQ buses. So the number of equations uh, will be formed by the specified real powers, that will be n minus 1 plus number of this reactive power, specified value of the reactive power, that will be n minus m. The total number of equations will be 2n minus m minus 1, and from that we can get these delta P2, delta P3 that up to delta Pn, and delta Qm plus 1 that up to delta Q1. That's for the PQ buses. Similarly, we have the variables. We have all deltas from bus number 2 to bus number n, and we have the voltages for all the PQ buses, that is bus number m plus 1 to bus number n. So these elements then can be found by simply derivating these equations with respect to variables. For example, the first row will be the derivative of the real power at bus 2 with respect to the all variables, that is all deltas and all voltages. Similarly, this row will be the derivative of the reactive power at bus m plus 1 with respect to all variables. So we can see that this matrix, this submatrix, that is J11, is the derivative of the all real powers from bus number 2 to bus number n with respect to the variable delta from delta 2 to delta n. This will be the matrix derivative of the all real powers from bus number 2 to bus number n with respect to the all voltage variables, that was bus number Vm plus 1 to Vm. Again, this will be the G21. This will be the derivative of the all reactive powers of PQ bus, that is from bus number m plus 1 to bus number n with respect to all deltas, that is from delta 2 to delta n, and this matrix will be the derivative of the reactive powers, that is Qm plus 1 of the PQ buses from the bus m plus 1 to n with respect to all voltages from the same number of buses. Now let us try to do a small example, and we will try to form this type of a matrix. Let us say we have a 5-bus system. Bus number 1 is the slack bus, bus number 2 and 3 are the PV buses, and 4 and 5 are the PQ buses. First, we'll try to figure out what are the different equations, and they will be definitely based on the specified values, and what are the different variables. हमारे पास जो variables होंगे that will be all deltas, सारे deltas from 2 to 5, that will be delta 2, delta 3, delta 4 and delta 5. And since PQ buses voltage is not specified, we will be having also V4 and V5. We can see delta V4, delta V5. So what are the different equations? That will be all real powers, that is delta P2, delta P3, delta P4 and delta P5, and the reactive power of the specified reactive power of the PQ bus, that is delta Q4 and delta Q5. So what will be the order of this matrix? We can get that order from this. Order will be simply the number of variables multiplied by number of variables. The total number of variables for this system will be, we have 4 voltage variables, magnitude variable, and 2 voltage will be, deltas will be 4, that is delta 2, delta 3, delta 4, delta 5, and voltage will be V4 and V5. That means there will be 4 number of variables, and equations will also be 4, which we have already discussed. So the order of the matrix, Jacobian matrix, will be 6 cross 6. The order of this matrix will be 6 cross 1. The order of this matrix will be 6 cross 1. You can get it from this also, because n is equal to 5, m is equal to 3, because m will be the total number of generator buses, that is including the slack bus, M will be actually equal to PV buses plus the slack bus. It will be always be containing all the generator buses. So M minus 1 is equal to 2, that is M minus 1 will depict the number of slack buses. So, sorry, number of PV buses. So 2n minus M minus 1, that is 2 into 5 minus 3 minus 1 will be 6. So from here also we can get the order of all the matrix. This will be 6 cross 1, this will be 6 cross 6, this will be 6 cross 1. So this have been written like this: delta P2, delta P3, delta P4, delta P5, or we can say these are the equations which we have found from the specified values of the real power, because real powers will be specified on all the buses except the slack bus. That's why here they started from delta P2. Similarly, real power will be specified with a PQ bus. Since the PQ buses are 4 and 5, it will be delta Q4 and delta Q5. And the variables here are delta 2, delta 3, delta 4, delta 5. That is, these deltas are unknown for all buses except the slack bus, and V4 and V5 will be variable for bus number 4 and bus number 5 for the PQ buses. So then it is simple. We have to form these elements by simply derivating these equation with respect to these variables. So this will be delta P2 by delta 2, delta P2 by delta 3, delta P2 by delta 4, delta P2 by delta 5. So this row will be the real power at bus number 2, which will be derivated for every variable which are over here. You can see it over here. But after this will be derivated only for all the variables in deltas. Then same real power is derivated with respect to the voltages. So when we proceed in the similar way, we have delta P3, that is this will be derivative with respect to all these voltages. Delta P3 by delta 3, delta P3 by delta 4, delta P3 by delta 5, delta P3 by delta V4, delta P3 by delta V5. Similarly, for the reactive power, that's delta V4, it has to be derivative for all the values of the variables. That is delta Q4 by delta 2, delta Q4 by delta 3, delta Q4 by delta 4. Similarly, up to this delta Q4 to delta V5. So from here to here, it will be delta Q5 by delta 2, delta Q5 by delta 3, delta Q5 by delta 4, delta Q5 by delta 5, delta Q5 by delta V4, and delta Q5 by delta V5. So the J1 matrix will be 4 cross 4, that's n minus 1 cross n minus 1. That is real powers derivative with respect to deltas. This will be real powers J1 to real powers with respect to derivative with respect to voltages, unknown voltages. This is the reactive power derivative with respect to this delta. This is the reactive power derivative with respect to voltages. This is n minus 1 cross n minus 1 is the order of J11. J12 will have the order of n minus 1 multiplied by cross n minus m, where m is 3, that is 5 minus 3 is 2. Here it will be n minus m, that is 5 minus 3 is 2, cross n minus 1, that is 4. This will be n minus m into n minus m, it will be 2 cross 2. Now homework for you is that you have to use the same 5 bus system. One is the slack bus, but the modification for this will be 2 and 4 will be PQ buses instead of 4 and 5, and 3 and 5 will be PQ buses, P buses instead of 2 and 3. So you will form this matrix, these 3 matrices for this system. I will see in the interaction class. So let us try to do one numerical based on the Newton-Raphson method. Consider a 3-bus system of figures shown below, that is this. Each of these lines has a series impedance of 0.02 plus J 0.08 per unit and a total shunt admittance of J 0.02 per unit. The specified quantities at the bus are tabulated below. This is the specified quantities. And the reactive power generation limit. It is not the reactive power injection limit, it is the generation limit. We have to calculate the injection limit. It is given in this form. So we can say reactive power is also specified within the limits. So find the load flow solution using an R method. So again we have to find out the different voltages and angles by using the Newton-Raphson method. First we'll calculate the Y bus. So impedance is given, we will calculate, since all the lines have the same impedance, we will calculate the line admittance. Line admittance is the inverse of the impedance, that will be like this. So in polar form, it will be 12.12 at an angle of minus 75.96. So off diagonal elements will be simply the negative of this, that is minus 2.941 plus J11.764, that comes out to be U12.14, 104.04. The diagonal elements will be there will be two lines, all the admittance connected to the two lines, and this shunt admittance will be divided into two. One will be connected at this, one will be connected at this. Similarly, it will have this shunt admittance, one divided into two, one will be connected at this and one will be connected at this. So the total admittance connected at this point will be this line admittance plus this line admittance plus half of the shunt admittance of this line plus half of the shunt admittance of this line. So it comes out to be equal to this 2 into, that means two lines are connected with this admittance, 2 into 12.12 at an angle of minus 75.96 plus this 2 should have been multiplied to both, because half of this is connected at this point, and this point it comes out to be again equal to 0.02. Here I have written at 0.01, but it should have been multiplied by 2 whole. So it comes out to be 24.23 at an angle of minus 70.75.95. So our y bus is like this. All the diagonal elements will be same and all the off diagonal elements will be same. So this is our y bus. So we'll first calculate what are the specified powers, injected real powers at different buses. So P2, that will be equal to, sorry, Pi will be equal to Pgi minus Pgi, Qi is equal to Qgi minus Qdi. This also we have discussed in the previous classes. So P2, when I is equal to 2, will be equal to Pg2 minus Pd2. So P2 will be equal to this Pg2 minus Pd2, that is 0.5 minus 0, it will be equal to 0.5. Q2 will be equal to Qg2 minus Qd2, it will be equal to this 1 minus 0 is again equal to 0, sorry, it's equal to 1, and P3 will be equal to Pg3 minus Pd3, it will be equal to 0 minus 0.5. This 0 minus 1.5, it will be equal to minus 1.5. Now this equation is given specified values of the generation of this at bus 3. So I will minus QD3 at every term. So it will be 0 minus QD3, QG3 minus QD3, 1.5 minus QD3. So this comes out to be equal to Q3. So when we subtract this QD3 is 0.6, QD3 is 0.6. So it comes out to be equal to minus 0.6 less or equal to Q3 and less or equal to Q 0.9. This is the reactive power limit which is at bus number 3. Let's now continue. Now for this case, since from this data bus number first is slack bus, it is given, bus number second is PQ bus, and bus number third is PV bus. So in this case, we'll first decide how many variables are there. At PQ bus we have voltage, that is delta 2, delta 3, and we have V2. Okay, we have V2. So we have discussed the variables, that is delta 2, delta 3, and V2, sorry. So what are the given values, specified values, that is P2, P3, and Q2. So going in the same way, you can see we have delta P2, that is the equation of which we can get from the specified values. At bus 2 we have specified values of P2 and Q2, that we have delta P2, delta Q, and delta P3. And what are the variables for this case? Well, in this case we will have both the deltas that are we found that are variables, delta 2 and delta 3. This will be delta V2 should be this. It should not be delta V3, because V3 is the PV bus, V2 is the PQ bus, where voltage are to be calculate. This is delta V2. So these terms will be delta P2 by delta delta 2, delta P2 by delta delta 3, delta P2 by delta V2, delta P3 by delta delta 2, delta P3 by delta delta 3, delta P3 by delta V2. Similarly, delta Q2 by delta delta 2, delta Q2 by delta delta 3, and delta Q2 by delta V3. So all these elements are to be calculated, and in this case there are 9 and these 3 are 12 elements are calculated to find these 3 values. So first we'll calculate delta P2. Delta P2 is P2 specified, the specified value of P2 minus P2 calculated. P2 is specified, which we have already calculated, that is 0.5, and now from these value we have to calculate this P2. Taking the initial values of the voltage as flat voltage profile, that is for unknown, V1 is equal to 1.04 plus J0, it is given. V2 is 1 plus J0, and V3 is 1.04 plus J0. So these unknowns are delta 2, delta 3, and V2. We'll assume their values to be, for voltage is 1 and for delta is 0. So when we put these value in this equation, voltage deltas and this admittance values of the Y bus, will get P2 calculated to be equal to minus 0.23. Similarly, we can get P3 calculated as 0.12 and Q2 calculated as minus 0.96 by assuming these values. So delta P2 will be equal to P2 specified minus P2 calculated. P2 specified is 0.5, which we have calculated here, and P2 calculated is minus 0.23. It comes out to be 0.73. Delta P3 will be P3 specified minus P3 calculated, that is minus 1.5, which is calculated like this. So it comes out to be minus 0.12, that is this value. It comes out to be minus 1.62. Similarly, delta Q2 will be equal to Q3. This will be Q2 specified minus this Q2 calculated, like this. So what is Q2 specified? That is 1.0, and this comes out to be 0.96, that is 1.96. These are the 3 values of this matrix. Now we have to calculate 9 values of this matrix. So delta P2 by delta P by delta delta, if you can check the previous equation which we have already derived for this, that comes out to be equal to minus Vi summation j is equal to 1 to n, where here one term has been I have forgotten one term, that is j should not be equal to I. Vg by aj sin of delta I minus delta j minus theta ij. So expanding this term, when I is equal to 2 will equal minus v2 v1 y21 sin of delta 2 minus delta 1 minus theta 1 2. This term will be 0 because it has been derivative with respect to delta. Delta is not there, it will be 0, plus v3 y23 sin of delta 2 minus delta 3 minus theta 2 3. Here all the values are given because initial values we have assumed, and some values are given. These values are given from the y bus. This is also from the y bus. This is the magnitude of them. We can say y21, which is perhaps 12.12, and this theta will be equal to theta 1 to y21. This one. Magnitude of this will be equal to 12.13, and angle will be 104. That is, this will be y12 will be 12.13, and theta 12 will be 104.04. So by putting this value, delta P2 by delta delta 2 will be equal to 24.47, and delta P2 by delta 3, that is delta Pi by delta G, that will be equal to this Vi Vj Yij, this sine of delta I delta J minus theta ij. This also I have derived, and for this I is equal to 2, J is equal to 3, it will be V2 V3 Y23 sine of delta 2 minus delta 3 minus theta 2 3. These two will be 0. V2 is given to be 1, V3 is 1.04, angles will be 0. Wait a minute. V2 is 1, V3 is 1.04, and angle delta 2 and delta 3 is 0. Delta 2 3 is again 104.04, and Y23 will be equal to 12.13. putting this value, you will get this value, that is minus 12.23. Similarly, proceeding similarly in a similar manner, we can calculate all the values of this Jacobian matrix, and I haven't shown those values here, but you can do it on your own. That's an exercise to you. All the other seven elements you can calculate. I have already calculated, but you can calculate and check whether you are right or not. So putting this value in the Jacobian and then multiplying, what I have done over here, I have taken this to this side, and this delta delta 2, delta delta 3, and delta v2 will be equal to this inverse multiplied with this. So that is what I have written over here. So taking the inverse and multiplying that to this, you will get minus 0.0230 minus 0.0654, and delta v2 is equal to 0.0890. This will be the value of this change in variables. So delta 2 for the first iteration, delta 3 and v2 for the first iteration will be the initial value of the variables plus the change in the variable which we have calculated right now. So deltas initially are assumed to be 0 and v2 is assumed to be equal to 1. It comes out to be this. This will be delta 2, this will be delta 3, and this will be v2. So now we'll calculate Q3, that is the value of the reactive power of third bus, which is a PV bus. So when we calculate it, for this iteration it comes out to be 0.4677, which is under the specified limit. You can see it from the specified limit which we have calculated, that is this. It comes out to be in the specified limit. So for this iteration, the bus 3 will remain as PV bus. The solution will converge. When the solution converges, then we have to calculate line flows, power losses in the lines, and slack bus power. So for this problem, only 3 iterations are required to convert the solution, and the converged value of the voltages and this voltage and phase angles are like this. V2 is 1.081 at an angle of minus 0.024 radians. V3 is 1.04 at an angle of 0.0654 radians. Delta 2, delta 3, and this V2. These are can because this is constant. And Q3 is minus 0.15, which is again within the specified limit. That is V3 will be again the PV bus. This is the slack bus power which I have calculated. You can also calculate by putting these values in the slack bus power formula, and then we can proceed for calculating the line flows and power losses. So that is after this, that is easy. After calculating the voltage, the procedure for calculating the line flows and power loss is same which we have done in the Gaussian method. So this is for the Newton-Raphson method. Let us have the summary of these two methods. We'll see how these two, what are the different steps that are to be taken while doing these methods. We'll start. You can see that summary or algorithm. This may sometimes help you in doing a program for these methods. We'll start from the Gaussian method. The first method, of course, will be data reading. What is the data that has to be available to us? That is the number of buses, number of lines, how many are the generator buses, and what are the number of the load buses. And then we go for the Y bus formation from this information. We should have the value of the slack bus voltage and slack bus angle. This is of course usually equal to 0. This may be close to 1, 1.01, 1.04, 1.05, but in most of the cases this is also taken to be equal to 1. PI and VI that are to be specified for all PV buses, that is from I is equal to 2 to M. PI and QI for all PQ buses, that is for I is equal to this M plus 1 to N. Initial guess for unknown value, that is delta is equal to 0 and VI is equal to 1 for unknown, where I is equal to this 2 to N and VI is equal to M plus 1 to N. Reactive power limit for all PV buses and voltage magnitude limit for all PQ buses. In the previous lectures, we haven't take into consideration of voltage magnitude, but voltage magnitude limits are also taken to be into consideration. This is the first step. Second is calculation of the QI for PV buses where I is equal to 2m. We have done this also. We have to first see whether this will remain the PV bus or not. So when we calculate it, after that we have to check the reactive power, whether the reactive power is within the limit or not. So we have to check this limit. If this is within this limit, then we have to calculate delta IR plus 1, delta of this. If no, and if QI is less than QI minimum, we have to make this QI R plus 1 is equal to QI minimum and then calculate the voltages. Because for this iteration, this will not be the PV bus, this will be the PQ bus. So here, not only delta, we have to calculate voltage magnitude as well. So that we have to calculate VIR plus 1, but using this value, QI minimum. In that case, QI will be equal to QI minimum. Similarly, if again it is not within the limits and it is greater than the QI maximum, then QI has to be taken as QI maximum and VI has to be calculated using this value. In this iteration also, in this case condition also, this PV bus is not to be considered as the PV bus, it has to be considered as the PQ bus. Then we have to repeat the step 2 and 3 for all PV buses from I is equal to 2 to m. Now when we have calculated these deltas for I is equal to 10, then we have to calculate the voltage for the PQ bus. So that is where PQ bus where I is equal to m plus 1 to n by this relation, which we had discussed earlier. At calculating all the voltage, we have to check then voltage for its limits. If it is within the limits, well and good, it remains as it is. If no, if VI minimum is less than is or equal to this, sorry, it has been slightly overdone. That means VI R plus 1 is less than, it has been shown in other way around. VI R plus 1 is less than VI minimum, then VI R plus 1 should be equal to VI minimum. And then or VI R plus 1 is greater than VI max, then VI R plus 1 is taken to be this. We are not going to take the calculated value, we are going to take the limited value of the voltage in that case. Now use the acceleration factor like this, then we use the acceleration factor. VR plus 1 is equal to VI R plus alpha into VR plus 1 minus 1. Repeat this step 4, 5, 6 for all load buses. So we'll do this 4, 5 and this step 6 for all buses, that's I is equal for all load buses, I is equal to m plus 1 up to n. Then we'll compute the mismatch of the voltage and deltas and the maximum one. Delta V max will be equal to maximum of VIR plus 1, and VIR will calculate all the mismatches of the voltage and see which one is the maximum. We'll take that maximum, and also delta max will calculate all the mismatches from the new value, updated value of the previous value of the deltas, and we'll take only the maximum value of that for PV bus and this for PQ buses. Checking for stopping criteria, then we will see whether this delta V max is less than epsilon and delta is less than epsilon or not. If that is true, then stop the calculation. If that is true, then we have to stop the calculation and we have to compute the slack bus power and the power loss and line flows. That is the usual procedure, that is the second stage. If not, if delta V max is greater than epsilon and delta is greater than, then we have to go to the step second, that we have to repeat it again and again up until we are matched with this. Okay, thank you. I will stop over here, and in the next class I will try to do the same thing, same algorithm for the Newton-Raphson method. Thank you.